Hello, everybody. Welcome back to another episode of Learn with Dr. G. That's me. Today, we're going to be doing some image analysis using machine learning and AI and Python and Visual Studio Code and PyTorch and just a bunch of other stuff. We're going to be talking about moon rocks and space exploration, since that is the theme of the month for me. Yeah, let's go ahead and get started. As a reminder, we do have a code of conduct that I expect you all to follow, as will I. Essentially, our code of conduct is just saying, let's be kind to each other. I will be kind to you, you be kind to me. We're here to learn, we're here to explore, and we're here to have fun. Today, we're going to be following along on one of the Microsoft learning paths, namely this one, classifying space rocks using Python and artificial intelligence. If you want to check this one out, you can head over to aka.ms/learnwithdrg/classify space rocks11. Hello, Will and Jorge. I am in the comments, so I will be checking that out. And actually, I just remembered there's another commenting place that I need to be in. So I will be over there as well. Let's see. Sorry, still getting used to streaming to all of the places. So let me just jump over there so I don't miss any comments over there as well. Oh, that's not working. Well, if it doesn't, okay. Oh, no, okay. I'll figure that out in just a second. But yes, I am here in the comments, so feel free to say hello, ask any questions, and we can explore together. So as I mentioned, this is following along in this learning path, and I encourage you to check it out. And what we're going to be doing today is talking about how complex and how just kind of like difficult it is for astronauts, humans, to collect the right kinds of space rocks, moon rocks, asteroid rocks, etc., in order to bring back to Earth, and then how complex the process is once we even bring them back to Earth. Buenos dias. Hello, everyone. So I wanted to chat a little bit about that first. When we think about how this whole process works and the point of it, right? The folks who are here on Earth are often the folks who are the most expert on moon rocks or on space rocks, right? They're the ones who get to sit in a lab and just like explore. Oh, someone just said they want to rock right now, which I know this isn't what you're saying, but did you know that you can actually like request space rock samples to like look at yourself? Anyways, sorry, we'll get into that in just a second. But what I was trying to get to was that the people who are here on Earth are the ones who are more expert in space rocks. And this is a challenge. We're going to see that in just a minute when we start to show all of the space rocks in our code. But this is a challenge because the space rocks look like Earth rocks. As in, I don't know about you, but me not being an expert in rocks, it is very, very difficult for me to know what type of rock I'm looking at, right? I remember when I was a kid in school, we would talk about the different types of rocks, and my mom happens to be a 4th grade teacher here in the US, which is around 9 or 10 years old, and that is when they do the like Earth rock lessons. So she knows a lot more about rocks than I do. But if I pick up a rock, I don't know, it actually could be a rock from space. I don't know if you knew that, but they are found all over our planet. They are more easily found in places like Antarctica or in a desert because they're going to show up, like they're going to contrast, the color and shape are going to contrast against the snow or the sand. But you could have space rocks in your backyard. You totally could. So I don't know about you, but I do not know how to tell the difference between rocks. And that is really complex when you then have to send a small group, meaning like, 2 to 5 people up to the moon to collect different types of rocks. The likelihood of those folks, those astronauts, being total experts in the rocks that they're collecting is small, because they also need to be relatively experts in, you know, rockets and in medicine and in first aid and in electronics and in like software and basically everything, because they're going to be kind of alone up there, right? So this becomes a really complicated problem. And that's kind of what inspired this lesson. Yeah, Arizona is a great place to find space rocks. I've heard the same. That's where the inspiration for this lesson came, because although this lesson is a very high level intro into using PyTorch and neural networks, we're not going to go into the total details of that. We're going to kind of, but we are going to actually do one. Even though this is a high level intro, what we're solving for is, imagine if we could have a rover that could, you know, go around onto the surface of an asteroid or the moon or another planet and decide which rocks they're collecting. Thank you. And so if we could have a machine doing that, then that could help the astronauts, because then they could focus on other things or what have you. It could also help the scientists here on Earth, because then they could maybe pre-classify, even if it wasn't the rover on the planet, but if it was just kind of like an image recognition here on Earth, they could pre-classify rocks down here. So let's take a look at some of these rocks. Let me share my screen again. And this is where we got all of the rocks from. How did this Classify Rock program get funded? I am building many machine learning models myself for animal biodiversity. Very cool. I don't know which specific rock you're talking, or program you're talking about. This stream in particular was just content that I am finding interesting in order to give an intro into neural networks and Python. And I just think that this problem, this, you know, is an interesting one to solve with it. I think the animal biodiversity, like using machine learning models around that, is super, super interesting. I'd love to learn more. A step-by-step instruction document, just to repeat it again after the session. Yes, you can definitely get that if you head over to aka.ms/learnwithdrg/classify-space-rocks, which is right there in the on the screen and in the chat. That's where you can find a step-by-step instruction guide. Lunar rock classification is pretty interesting. Yeah, I agree. And by the way, this is where, let me just grab this URL for you all. This is where you can actually request samples, which I think is just so neat, particularly if you are like a student or a teacher. You can request samples for your students and also like for public displays. But if you want to study rocks, I just think that is so cool. But in any case, you can also head over to the collection, which is here. This is the Lunar Sample and Photo Catalog. And from here, we will be able to see all of the images of the lunar rocks that were collected across all of the Apollo and Luna missions, which I think is really neat. We can see that there are 5 different types or classifications of rock: basalt, crustal, breccia, soil, and core. And then there are some other things like minimum weight and maximum weight, and then pristine sample available, percentage of pristine sample available. And this is kind of interesting. We did another Learn with Dr. G session on predicting how many samples of rocks the, and now I'm blanking on the name. Oh gosh, darn it. The next mission that's headed out in 2024, not Apollo, because that's the one that already happened. Artemis, there we go, another A. The Artemis mission, which happening in 2024, we did another one on predicting how many rocks we could collect there. In this case, we're just going to try to classify the rocks that we have or might collect. And why? For me, the reason why I think that's important is this minimum percent pristine from original weight, I think, is particularly interesting. To me, that shows us which rocks might be of most interest to the scientific community. And therefore, if we could collect more of those types of rocks, then maybe we can continue to conduct more research on the topics that we're interested in. So that's kind of how I think about it. But we can take a look at, for example, all of the Apollo mission or Apollo 11 rocks. And when you come in here, you basically just get this huge database where each rock is here. So here is sample 10001 from Apollo 11. It was in this bag number. This was its original weight, 125.8 grams. It has been classified as soil and unsieved. Here's additional description here. There's 88.36% of this pristine sample left. And this was calculated on January 10th, 2008, which I believe just basically means that that no one has taken from this sample since then. There are display samples available for this one. And then you've got kind of the more information here. This one doesn't actually have an image of it. But if we head over, oops. Oh, that's opened up a new one. If we head over to, goodness gracious, samples catalog, sample photo database. You can also click on, here we go. We can also search just by images. Is this not working? Are they ever going to get massive hunk of metal that is apparently floating out there? Because I'd love to smolder that. That would be awesome. Imagine like creating a sword out of space metal. Like that would be so epic. Yeah, I don't know. View samples by image. Okay, here, let's search this way. There we go. Okay, where's the, nope, that's the same place I was just at. Display samples. Here we go. So here's an example of a sample that does have a display, as in it does have an image. No, this is the, sorry, I'm getting so confused. Why am I getting so confused? Where did my images go? Here's my images. Okay, that other one just didn't have an image, which is what I thought. What I was just clicking on was where it's displayed currently. So for example, Apollo sample 10,017 had 973 grams. It was a basalt. There's 43% left of it. And if we scroll down here, we can start to see images of that sample. So we can see this image right here. Here's that sample. And there's a few things to note about not only the images, but the samples themselves. Number one is that the samples do have like a film around them, not like a film necessarily, but like a layer of, or multiple layers of stuff. It might be other like, rock type things. It could just be that dirt and dust. I don't know the technical terms there, but it's not clean, right? And that's a challenge. It's a challenge because we need clean images to be able to tell the difference between two rocks, right? Another challenge is going to be that the rocks are not going to be in like, a really well lit Instagram style picture with like a clean background and all of the edges and everything really clearly displayed. Someone's asking about a Microsoft project Natic. I actually don't know about it. That would be cool if we could launch a data center into orbit for NASA to use. I don't know about it though, unfortunately. And do you train the AI to scan the picture only in the box? Yes, we are going to train the AI to scan like a small portion of the picture. I'll show you that in just a second. These are all of the challenges, right? Because like this does not just have a picture of the rock. This also has a picture of the thing that it's inside of. And, this picture has some flash on it. So that coloration is going to be very different. Also, it's black and white. So that's going to be very different, right? If we start to look over at some other ones, for example, let's go into Apollo 17. Some interesting things here is that once we get to later missions, we can actually choose which station and or landmark the sample was collected near. So that's kind of neat. But let's take a look over here and see if these ones, so these ones have some samples as well. We can see that, again, we've got shadows. They're not like the best pictures because the point of these pictures wasn't to be able to create machine learning and AI to classify them. The point was to, just to have additional information like metadata around the samples. You can see that this is part of the sample, which has it kind of taken apart. This time we do have some additional kind of metadata with this square here, and we can start to see a little bit more of the shape because it's against a white background. So that maybe gives us a little bit better data. I think a deep learning approach could be used to predict for the prediction of planets with conditions similar to the Earth using the radiation spectra emitted by these or other features. I agree. I think that is why space rocks are super interesting to me. You can drill into a rock and then take a picture of the rock from the drill sample to identify it better. Yes, I completely agree. And imagine you could actually have a rover potentially do that, right? It could collect a sample, it could drill in maybe with like a clear drill bit and pull it out, and then maybe it could be clear, and then you could take picture and actually identify some pieces. I think that's super interesting. Is there data from Spectral Analysis one of those rocks look like Jello? I agree. I don't know. There might be some additional information. This database is humongous, and we didn't go through every single thing, so I'm not entirely sure. What we did do for the purposes of this lesson is just gather the best pictures that we could find that represented two of the types of rocks that we wanted to classify between. Again, because it's mainly an intro, but everything that y'all are saying in the comments is exactly the reason why I wanted to make this intro, because this is just kind of the start to where you could then go even further. Is there, it would be nice to see what characteristics are considered to say that a planet has conditions similar to Earth. I completely agree. Please continue to put your imagination to fly. I love it. Another question, could you use the image scanning capability of HoloLens for this too? That would be really, really cool. I hope so. I have not obviously tried that yet, but like that would be really awesome. Are there jobs at Microsoft where you get to build models? And totally agree with the spectral analysis. Why not use multimodal solutions? Yes, I completely agree. Yes, I believe that there are. I am not in kind of that org, but yes, we do hire machine learning experts who do build models. I don't know if they're actively doing anything on moon rocks, but yes, that exists. And yeah, I completely agree. I don't think that there is one solution to these things. And as we start to understand the limitations, for example, the fact that there's layers around it and maybe we should grab, a core sample instead, then now we're kind of understanding at what point we can use different parts of the solution to be able to create a complete picture. Right. And it also depends on what kinds of questions we're asking. So if we're needing to get an answer to what type of rock is this while we're standing on the moon, then we need a very different set of approaches rather than just needing to know how many we've collected entirely. Right. Did we find gold on the moon rocks? I don't know. I have no clue. If anyone knows if we've found anything like that, please share. And if you are interested in this type of thing, I did want to highlight this, and we do link to it from the lesson. But this is the OSIRISRex mission, which is a specific mission to collect samples from asteroids. In particular, the asteroid that they're collecting from is called the Bennu, and it's so the OSIRISRex is a spacecraft that's traveling to that asteroid that's going to be collecting samples from it. You can read more about it here, and there's actually a neat timeline here where we can see that this month is when they are finishing orbital R, and they're going to start to go into the second phase of the reconnaissance, which is continuing to do some flyovers, and eventually they're going to have a rehearsal to see how they can get it onto the asteroid without it kind of getting kicked off, as you can see here, and then hopefully do this kind of touch and go where it's just going to grab a bunch of sample as quickly as possible, like, touch, grab, go. I think it's so cool. Anyways, probes that go into asteroids, and yeah, so yep, we were just chatting about that. Once your model is built, how do you turn it into a PFGA? Yeah, we're going to talk about that in a little bit. And there's other rare metals worth more to be found in orbit. Yeah, exactly. And sorry, just total side note, worth more. I feel like in today's world just is like, it makes me laugh a little bit. Like, yeah, I would definitely pay more for like a like something made from something from space, because that's so cool. Ways to transfer data from deep space research back to Earth or the ISS. Yes, I have not personally thought about that. Well, I mean, I've thought about it like anecdotally, but I am not an expert in it. But yeah, we were chatting about that on last week's stream. If you missed it, you can check it out on pretty much any, like wherever you're watching, there's probably a link to it. But we were chatting about that because the time it takes to get information to and from even, you know, like, well, the moon or Mars or the ISS is a lot more time. So how can we kind of solve for reducing that time? The Expanse. That sounds interesting. Author Terry Pratchett was knighted by the Queen of England with a sword he had forged from a meteorite. That is a really cool tidbit. Thank you. I appreciate that. This is why I love doing stuff around space, because we could just talk about really fun stuff. Cool. Yeah, so I mean, that's kind of like where we're starting from. We can see that the samples are pretty hard to get like really clean ones, but we are going to start with that. And what we talk about in this this learning path, which consists of 4 modules. The first one is basically talking about why, kind of what we just chatted about, like why space rocks are interesting, what are the challenges around them, etc. The second one, we do make sure that you get all of your Python libraries in order, and I can show you quickly what I did to do that. And we talk a little bit about how we might classify rocks, both like a human, how we would do it, and then how a machine might. The third one is where we actually go in and analyze rocks. So we're going to do that together in just a minute. And then the fourth one is actually building our neural network and testing it. So that's what we're going to do for the second half of this stream. I'm going to check on thinking about it now, data and space transfer. Yeah, I'm super curious about it. I remember now there was like some tweet about it. There's been too many. So, but yeah, actually I'm going to write it down too, because I want to remember that. There was something. Cool. Writing it down. Awesome. All right, so let me pull up let me bring this over here, and I'm going to bring up, and we're going to go ahead and we can do this together. I do not want that in my data folder. Okay, so what did we do to get started here? So this is, come on. I'm just going to switch this over. I don't know why it wants to. Yes. Okay, here's my Visual Studio Code. I don't know why it started acting all funny, but I do have Visual Studio Code here. And Azure Orbital. Oh, that's what it's called. Okay, we'll definitely have to check that one out. Here's Visual Studio Code. And the way that I set this up was by using Anaconda. So I have this Anaconda prompt, which, there we go. Basically what I did, I can't find my scroll, is I created a new Anaconda environment, and all of these are in that Learn module, which is down here at the bottom of the screen, aka.ms/learn with Dr. G /classify space rocks 11. Connecting satellites with Azure, sort of like express routes, direct connectivity. That is so cool. Yeah, I want to check out Azure Orbital now, because that would be really neat to see how it would play a role in like discovering things about space. So we created a new Anaconda environment with Python and a bunch of different libraries that we need to be able to do this neural network. And what Anaconda is basically creating a virtual environment for us. So then that way, whatever Python or whatever libraries we have on our machine, we don't have to mess with any of that. We don't have to have it be just like a huge environment. We can have specific small environments for specific projects. So we're going to do that here. Once you create it, you say yes, yes, yes. Then you need to activate your environment by doing conda activate and then the name. And then once you have done that, did I skip it? Here we go. We do want to make sure that we're installing PyTorch and Torch Vision. So make sure that you have that in there. Particularly, we want to be able to change like the sizes of images and things, which we'll get into. And so once you've done that, everything should be ready to go, and you should be able to open up Visual Studio Code. You should be able to create a new file with a .ipynb extension, which is a Python, interactive Python notebook or like a Jupyter notebook inside of Visual Studio Code. If you have the Visual Studio Code Python extension, then this should open up in this format here that looks like a notebook, where we have cells that we can write code in. We can run each cell individually, and then we can do all of the notebook stuff that we're used to. If this is new to you, we do have a bunch of videos on this. You can check out my previous video, kind of wherever you're at is probably there. If you did just create a new environment, you might want to switch over to be using that new virtual environment. So you can do Control-Shift-P or Command-Shift-P and find Jupyter. If you start typing Jupyter, select a kernel, and that'll bring up the list of all the kernels. And I'm going to be using the myenv one, which is the one that I created earlier. All right. So now that we have our environment set up, we are going to make sure that we have all of our libraries imported and bring in all of our images. So to find our images, they are right. Let me grab those for us. Here it is. So we do have all of the images on an Azure Blob storage that you can download the zip file for. You can find the link to it inside of the module. And what we're going to do is import both the libraries and then also the images. So I've already downloaded the images. They're in this folder called data. And I have two subfolders in this folder called data, one called basalt and one called highland. And the basalt basically has the images that we chose to download from that database. And you can see that we chose these ones because they are kind of the cleanest ones, the ones that don't have a lot of other kind of like equipment or a desk or things like that. They're the ones that have already been cleaned for the most part. And they're ones where we can, they all have kind of a similar lighting and they all have a similar size of the rock in comparison to the image. And they also have they're also ones that show off the features kind of the best. So we can see that it's got like certain features and like lines and things like that. So these are what basalts look like. Highland or Krustal look like this. We can see that some of these, they're all going to kind of have this similar thing. Again, all of the images are different. So it's really hard to get all the same. And when you are doing a machine learning or data science project, this is where it's really important to think about how you're collecting data, how you're storing data, and then what data you're using. And you're not always the same person who can collect the data and store the data versus the one who will use it. And so in this case, for example, I can't just call up NASA and say, hey, can you go through your thousands of samples and retake all of those pictures with a high quality camera from 2021 and good lighting? Here, I'll send you a ring light. Like we can't do that, right? So we have to kind of handle it with what we have, namely the images that are here. So these are all of the images that we have to work with that kind of show the difference between the Krustal images and the basalt images. All right. So the first thing that we're going to do is make sure that we have all of the libraries that we need imported. So we're going to import Matplotlib, specifically PyPlot. And this first one is the one that, like, we always knock on wood to make sure. Oh, come on. Why is this? I literally just did this. This is what I love about live coding, right? Like, we literally just did this. Why are you sad? Yeah, this is my environment. Don't be sad. Don't be sad, Python. We can do it. Why are you? No, you don't. You don't need that. You don't need that because we just did this. And then you're going to give me an error. I have not had an opportunity to figure this part out yet, but that's okay because I literally just ran it and it worked perfectly fine, which means I do have another file right here because I don't know why it's crying at me and I don't want to spend our last 20 minutes trying to figure that out. Always run it just before, just in case, make sure everything's working. I don't know why it's crying at me, but it's fine. So we're going to import Matplotlib, specifically the PyPlot, so that we can show things off inside of the Jupyter Notebook. We need NumPy. It's a very common library in data science, specifically for Python. We're going to import all of the torch things that we need to build our neural network, as well as our torch vision. And this is going to help us modify the images. Can this cover 3D scanned images, 2D, or both? That's a great question. I believe we can do 3D because what we're going to end up doing is basically converting our images into numerical data. So the three-dimensionality of an image really doesn't matter if it just means that we're going to have additional data. Conda environments are the best if they work. Okay, so basically the first 6 cells of this are just bringing in all of the libraries that we need. What we're going to do next is bring in our data. And in previous streams, if you've been watching any of mine, we tend to use scikit-learn, and scikit-learn already has a split test train data function for us. So we don't really have to worry about it. Could you convert a 2D into 3D? That's a good question. So the question is, can we convert a 2D image into a 3D image? And I mean, yes, but you're missing data, right? Like you're missing information. So if you just imagine that, I took a picture of this sticky note book, and you couldn't really see how thick it was. Yeah, we could turn it into a 3D. We can infer the shape of it and the kind of the 3D-ness of it, but you wouldn't actually know that it's that thick, right? So if you didn't have additional data to tell you what the 3D-ness would be, then you are inferring a lot of information, and therefore it may not be an accurate representation. It may not be like an accurate 3D representation of a 2D object. But yes, you can do that. And whether or not it would be important, I think that kind of depends on just the question that you're asking. In this case, it could be because the shapes of the rock might matter, the size of the rock might matter, but we would need to have that additional information. And having a 2D or 3D comparison, it probably would make, if we had 3D images and all of that data, it would probably make our AI more accurate, more intelligent. So yeah, here's where I was talking about, not only are we going to be building this function, that is the load split train test function, which is kind of like the biggest component of machine learning, where we take all of our data and we split our data into training data and testing data so that we can train our model on our training data and reserve our testing data to test our model on. But we're also going to take this opportunity to ensure that all of our images are exactly the same size. Yeah, if you had a sample, partial sample, yeah, no problem. Thank you for asking questions. I appreciate it. The reason why we want to make sure that all of our sample or all of our images are the same size is because it makes the difference between the images more accurate for the machine learning model, right? The size of an image is not actually relevant information to the shape or composition or features of the space rock. If the size of the image was relevant, then we probably shouldn't resize them, but it's not. So in this case, we just want all of the images to be the same size. And that way, when we translate our images from an image to numerical data, we'll be able to compare kind of apples to apples when the machine is looking through the data and trying to decide like what part of this image is being represented. What does that all mean? Because I feel like that was not a great explanation for that. And I just had a good, here it is. So this is an example from the module that we described. So we're going to take our image, for example, here's an image of Abraham Lincoln, and we're basically going to convert it into the individual pixels, and individual pixels can actually be represented by a color code. This is the Apple Banana Orange did an AI bootcamp in 2019. Awesome. Yeah, so this was actually a homework assignment from when I was in undergrad, where we took an image and we did actually read in each pixel and the color of that pixel. And then we used that to do interesting things. For example, we would actually do like build a green screen effect using that, because you could look at a pixel and if like the green was above a certain threshold, then you know that that was the green screen, not the person. And therefore you could replace that pixel with the equivalent pixel on another image to like fill in the background. So this idea that an image is literally just a bunch of pixels, which are literally just a bunch of colors, which can be represented as numbers, that's basically what we're doing here. So we want the image sizes to be the same. So then that way we just kind of have the same size array, essentially, or list of numbers, which is pixels, colors. Cool. Won't resizing distort the image, like affect the image resolution, or are you cropping the image when you're resizing it? That's a great question. I believe the majority of the pictures that we took from this one, we were actually, they were actually pretty much the same size anyway. So yes, you do want to be careful about distorting your image or affecting the resolution. That is a really, really great point. In this case, because our images are pretty simple, they all kind of like look the same, and the sizes were already pretty much the same. We're just kind of cropping them off. Great question, though. All right. So we're going to build up this split train test. I'm going to try to zoom out just a little bit so maybe we can see it a little bit all together. And this is a pretty extensive function. Again, we're not going to go into the details of building the neural network. I'm trying to just kind of encourage you to see what's next and continue to learn beyond that. But basically what we're going to do is we're going to first take images and we're going to create we're first going to create a transform, which is what's going to be applied to the image to then change it. So this transform is basically going to choose random images, choose random areas of the within this area. Oh my gosh, choose random areas within the image to crop to this size. And we're using libraries to help with this. I am not an expert in this part of it. We're then going to grab images from the data folder, and we're going to apply those transforms to those images. And then we're basically going to get a list of the indices of the images, and we're going to shuffle them up, and we're basically going to like split them up into training indices and testing indices. And then we're going to create a sample of images from the training set and a sample of images from the testing set and load those into Torch and return those loaders to be able to load certain images from training and testing that have already had that transform applied to it, which resizes them and makes them all the same. Goodness. What we did here then afterwards is basic. Oh, and by the way, we are going to take 20% of our data is going to be reserved for testing. So we did call that, save those into train loader and test loader. And then 20% of our data then is in test loader, 80% is in train loader. What we then do here is transform a new image into numbers and resize it. So that's what we're doing here again. Oh yeah, this to tensor is what transforms it from an image to those numbers. I forgot to mention that. Are the image classes evenly distributed? Yes. Yes. We're going to then get a build a function that selects a random set of images. So we're going to go into our image folder. We're going to apply the test transform to it and basically grab shuffle all of the indices again and grab a random set up to our num, batch size up to num, and create a loader just for that one set of random images. And then we're going to return all of the images and their labels. And what this allows us to do is basically go in and grab a random set of images. For example, here's our random set. We can see that since we did just crop things, that we did potentially crop some rocks out of the images. Again, this is not the best, like most authentic way you should do these things, but rather a way to start to explore how we're doing them. All right, and this is basically just grabbing a certain number of images. So we're going to grab 5 random images, and we're basically going to get those back and put them into like a figure and plot them out. It's not like plotting, it is plotting, but you know, just put them out so we can actually display them within our notebook. Yes, Anaconda or Miniconda also creates those environments for you as well. So you could just use a container at that point, since it is the cool thing to do. Yes, you totally could. Yes, there are often things installed that you don't need. It all, I think there's a lot of preferences, not just personal preferences, but based on projects or what you plan on doing next and things like that. This now is whether will help us determine whether or not we're using a CPU or a GPU to build the deep learning network, and then helping us to actually be able to use Torch to create the models. Is there a way that we can avoid cropping or resizing the images without affecting our model accuracy? Yes. I mean, what I would encourage you to do is take this as your starting point and see what happens if you don't crop them at all. Or take some of your own images and see what happens with the differences between images that have a lot of like blank space or don't have a lot of blank space or have like varying sizes. So I encourage you to check that out. But yes, you definitely can not crop images. It just has a lot of trade-offs for how hard it is. If you have the uncropped images, then it might be harder for the machine to learn and then have a more accurate model. But you might want it to be more accurate. And so even if it's harder and therefore takes longer and takes more data, it might result in better accuracy, therefore making your model like more effective. And that might be most important. So yes, great question. This is where it starts to get interesting. And this is a bit beyond my expertise because I am not a neural network expert. But basically what neural networks are. And we have this really great, let me bring that up. We have a really great way of showing this. Build a neural network. Because this is the step that we're on now. So basically what's happening is we are going back and forth across all of our data and the information that we have about our data in order to essentially build a brain, right? Like that's why we call it a neural network. It's like neurons and nerves and things like that, right? So you're basically making connections between what we know is true and what we're seeing, we being the machine, over and over and over again until it's accurate, right? And if you really think about it, it really is how we learn. There was actually a really interesting group of researchers at UCSD. This was like 15 years ago, when they were first starting to try to figure out, I mean, not first, but early days of AI. And I remember because they were one of the first, many other people did as well, but they were one of the first folks to think, you know what, rather than trying to get a machine to be as smart as a human, adult human, why don't we help machines learn as humans learn? So the machine needs to learn as a child would learn. And I'm the parent of a 3-year-old, and this repetitiveness of, is this right? Yes, it is. Is this right? No, it isn't. Is this right? Yes, it is, right? The repetitiveness of learning to write letters. She's just learning to write her name and, doing an A and then getting, information back. Yes, that's an A. That repetitiveness is exactly what these machines are doing when we're training machine learning models. I just think that is so cool to think about it that way. I may not be an expert machine model person. I may not be an expert in neural networks, but I love understanding kind of the way in which we're helping machines to learn. And then because they're machines and because they can see more detail than we can see, and because they can do things much faster than us and store a lot more information than us, because of all of that, they'll be able to surpass us quickly in terms of being able to make a decision on something. Again, whether or not that's the right decision and biases and ethics and all of that is a huge conversation we've had many times. Watch previous videos. We'll have it again, I'm sure. But just kind of the fact that if we start teaching machines like they're kids, like they're babies, like we do to humans, they can then do some really amazing stuff. I think that's fascinating. So what we're doing with this code that I was just showing is basically building the neurons and wiring them in the appropriate way. And we're not actively doing that. The machine is doing that. We create parameters and suggestions for how it should do that based on the data that we have and the questions that we want it to answer. But it's basically wiring the neurons. And I just think that is so cool. The chat is working. I can see you. Hello, person chatting. Awesome. Okay. So this is basically that code that goes through, and we're just using the PyTorch neural network classes, and we're building up our deep learning model and helping it to make connections between things. The next thing that we need to do is actually train our neural network on our data. And this is, we're out of time already. So this is a huge thing. Lots of details. I am not an expert in this part, but I'm learning it by building things based on examples and slightly modifying things. Does this need to be run in Azure, or can it be run locally on a powerful PC? I am running this all locally using Visual Studio Code. This does not have an Azure subscription associated with it. I'm not running anything in the cloud. All I did was download free Visual Studio Code, free PyTorch, free Anaconda, free Python extension for Visual Studio Code, and I'm running it on a Windows device. Hello from a fellow machine learner. Hello. For the code, oh yeah. And then chat is working. Some viewers are on YouTube. Yes, sorry. If it's confusing for you, we're streaming to 3 YouTube channels and 2 Twitch channels and Learn TV. And the Learn TV chat, I messed up today, but every other chat is totally working. So what we're doing here basically is going through and this piece right here, this line, and I'm going to probably mispronounce it. I call it epochs. Epochs? I don't know. I don't know how to properly pronounce it, but it is like a neural network term. It's basically how many times the like model is going to be searching for associations in features. We're setting it to 5 now. If you increase that number, you will make it more accurate, but it's going to take much longer. So that's why we stick it to 5. So what this is basically doing is going through and training our model on our training data using the neural network that we created. And after we train it, we can test the accuracy based off of our testing data, that test loader that we created. Epochs, maybe that's right. How do I verify that an image classifier is not overfitted? That is a really, really great question. I think one of the biggest ways to verify whether you're not overfitting is to make sure that your testing data has authentic, accurate, like information, examples. And if your if your training data works and then your testing data has more authentic and accurate and not the same data from your training data, then if it has a low accuracy, it's probably not great. It's a really complicated question. I'm sure there's much better explanations and much more nuance to it as well. And then we can save our model. When we're using PyTorch, we literally just have to say save, and we can save it to this PyTorch function or file type. And once we do that, we can send in an image to predict. So what we do is we create this function that sends in an image file, and we apply the test transforms to the image, which will not only do that cropping, but also turn it into numbers. I don't actually know what the Unsqueeze does. So if anyone knows what that does, feel free to share with me or share with all of us. But basically what we're doing here is we're going to have this image be input into our neural network and then predict the index, meaning whether it was basalt or crustal/highland. We can get 5 more random images. And we can just go through, and for each image, we can predict whether or not, right here, the predict image, it's a basalt or a highland or crustal. And so we can see here that of these 5 random images, for basalt, these are all basalt images, and we only got 1 that was predicted incorrectly. Sorry, these are not all basalt images. These 4 are basalt images, and we predicted them correctly. This one, we predicted it was basalt. It's actually not. It's crustal/highland. So yeah, that's how you can start to explore classifying images from space rocks, all with free tools, all on your local machine, assuming that your machine is relatively powerful enough, and some of the considerations that you might want to take into account when you're doing so. As we wrap up, I do want to remind you all that we do have this really quick survey, aka.ms/reactor/survey. And if you wouldn't mind taking this survey and putting in the code 12535, it helps us to see if this is the kind of content that you want to keep seeing. And if so, then I can continue to make it. And if not, then you can let me know what kind of content you're interested in. And I just accidentally covered that up. There we go. So I encourage you all to check that out. We can continue the conversation on Twitter. I'm at Dr. Guthels or #LearnWithDrG. Everything that you're doing, that you're learning, that you're checking out, that you're experimenting with, like, I want to know about it. If you did this exact same Learn module and you completed it and you're like, I did it, that's awesome. Tell me about it. I'm excited. I will celebrate with you. If you went beyond this and did something way like cooler or just more in depth, I also want to check that out. And if it's just somewhat related and you want to continue talking about the different, space exploration or Azure Orbital, please, let's keep chatting about it. So feel free to reach out to me. Otherwise, I will be back next Tuesday, same time, and we're going to be talking about predicting rocket launches. Yes, predicting rocket launches using data science. So if you want to check that one out, make sure you stick around for next week. Otherwise, thank you all so much for joining me, and particularly for engaging in the chat. These live streams are way more fun when people are having fun with me. So continue to do so, and I will see you all later. Have a good one. Bye.